We just killed Google TurboQuant. Today, we're introducing SpectralQuant, 5.95 times KV cache compression for any transformer, with essentially zero accuracy loss.
Quick rewind. 6 weeks ago, Google Research published TurboQuant. The claim, transformers running with 6 times less memory, 8 times faster, zero quality loss, and the stronger claim that this was mathematically optimal, the best anyone could ever do. Provably. The markets reacted violently. SK Hynix down 6%, Samsung down 5%, Micron bleeding 7%. Wall Street did the math. If Google really cracked optimal KV cache compression, the world needs less high bandwidth memory, a lot less.
So we read the paper, and it works, but it's leaving a lot of performance on the table. And the mathematically optimal claim turns out to hold under one specific assumption that no real model actually satisfies. So quick context for why anyone should care. KV cache is the scratchpad a transformer keeps as it generates text. Every token it writes, it scribbles down, so it doesn't have to reread the entire story to produce the next word. You can think of it almost as context. The longer the conversation, the bigger the notebook. The notebook is the single biggest reason why production AI is so expensive to run.
More context, more users, more streams, all measured in gigabytes of high bandwidth memory that we didn't have. That's the wall. That's why TurboQuant mattered. That's why we cared. Here's the part nobody expected. Sentra is not a compression company. We work on organizational memory, building brains for companies from their own knowledge. While building those brains, we were working very closely with embedding spaces, and we repeatedly started noticing something strange. These embedding spaces were advertised to be 384 or 1024 dimensions. However, all the signal, the variance, seems to be just in 16 dimensions. Picture a city advertised to have 1,000 blocks. You move there and you realize every building is crammed into 16 blocks. The other 984 blocks empty. Once you see this in one place, you start noticing it everywhere. So when Google's paper came out and we were thinking about KV cache, we already had a hypothesis. The cache probably is another empty city. We measured Quen, Mistral, and Llama, 128 dimensions per attention head, the same answer everywhere. Only 4 to 6 channels carried real signal. The other 120 plus noise. Same empty city, different buildings. Now go back to TurboQuant. Their main move is to scramble the information across all dimensions using a random rotation matrix and then shrink everything uniformly.
You can think of it this way. Imagine hiring a moving company that blindfolds itself. They throw your TV, your books, your dirty socks, your trash, all of it into random boxes and ship them. It sounds insane, but TurboQuant's math proves that on average, no box is overweight, no matter what's in your house. Their guarantee is your worst case proof. The problem here is that nobody ever asked whether the boxes were carrying something valuable or just junk you would have thrown out anyway. TurboQuant's optimality is insurance against a problem real models don't even have. It assumes that every dimension is equally important. Real attention heads put 80% of their information in 4 out of 128 dimensions. The empty city fact breaks the assumption. So the optimality claim doesn't even apply anymore.
The fix writes itself. Don't rotate randomly. Rotate using the eigenvectors of your actual KV cache distribution, which tells you which direction carries the signal. About 80% of information lives in 4 to 6 of 128 dimensions. We confirmed it across 12 production models: language, vision, protein, video. The math for optimal data-aware rotation has existed since 1947. Calhoun-Love. The math for spending bits where the information actually lives has existed since 1971, the Shannon-Bergen rate distortion. Both pieces are old. Combining them with selective error correction, calibrated per model in 15 seconds, that's the new idea.
It all comes down to 3 steps. First, calibrated rotation. We use eigenvectors of your KV cache, not a random matrix. Second, high precision on 4 signal dimensions. Low precision on the 124 noise dimensions. Bits go where the information actually lives and matters. Third, selective error correction. Google applies it to all 128 dimensions per token. We apply it to only 4 of them that actually carry signal. 32 times fewer dot products and the same accuracy. It's a 15-second one-time setup with calibration on a single GPU. No fine-tuning, no model surgery, and no retraining. And it's the same algorithm, 4 model families, and it wins every time. We took Mistral 7B at 6 times compression. TurboQuant added 22% perplexity. We added 7. That's 3 times less degradation.
25% closer to FP16 than the mathematically optimal baseline just by peeking at the data. Qwen 7B, 9.6 percentage points better attention quality. VIT large for vision, 9 points better at extreme compression. ESM2, the protein language model behind AlphaFold class structure prediction, 11 points. VideoMAE on kinetic 400 action recognition at 9.5x compression. SpectralQuant matches FP16 exactly. TurboQuant doesn't. Language, vision, protein folding, video, same algorithm every time.
Which leaves us with an uncomfortable geometric fact. AI lives in a much smaller space than it pretends to. And it shows up 2 different ways in our work. In a memory system, so what Sentra builds, the empty city is a bug. It's literally why models forget. It's why they hallucinate. The space they're using to store knowledge is much smaller than they think it is. But in a compression context, the same fact is a gift. If only 16 blocks of the city are real, you only have to pack 16 blocks. So the lesson, if there is one, stop ignoring the shape of what your model already learned. Look at it first, then build around it. If you're running TurboQuant today, the migration is 1 import line. It's the same function signatures, same kernels, same calibration cost. 15 seconds. We're already running it inside our own inference stack. 6 times more concurrent users on the same hardware. Quality is indistinguishable from FP16. SpectralQuant is open source today. PyPy this week. Any transformer with attention, so language, vision, protein, video, drop it in tonight. Free up half of your KV cache. Lose essentially 0 quality.
And if you're wondering why a memory company is shipping a compression algorithm, this is just the beginning. All of it comes together when you're trying to build brains for companies from their own knowledge. SpectralQuant is a result of a unique geometry that we observed. There are many more that we have observed. Try it. Let us know what you think about it.